Start the workshop by introducing our distinguished speaker, Professor Stephen J. Wright. So he will deliver two distinguished lectures. So let me give an introduction to Steve Wright. So Professor Stephen J. Wright held the George P. Danzig Professorship, the Sheldon Lobar Chair, and the Amma and Belinda Sohai Professorship of Computer Sciences at the University of Wisconsin-Madison. His research is in computational optimizations and its applications to data science and many other areas of science and engineering. Prior to joining UW-Madison in 2001, Professor Wright held position at North Carolina State University's and Argonne National Lab. He has served as chair of the Mathematical Optimization Society from 2007 to 2010, and as a trustee of SIME for the maximum of 3 terms from 2005 to 2014. He's a fellow of SIME. In 2014, he won the WRG Baker Award from IEEE for Best Paper in an IEEE archival publications during 2009 to 2011. He was awarded the Kacham Prize by the Informed Optimization Society in 2020 for lifetime achievement in optimization, and received the NeurIPS Test of Time Award in 2020 for a paper presented at that conference in 2011. Professor Wright is the author or co-author of widely used text and reference books in optimization, including Primordial Interior Point Methods and Numerical Optimizations, which was used as a textbook in our course. And he has published widely on optimization theory, algorithms, software, and applications. Professor Wright served from 2014 to 2019 as editor-in-chief of the SIME Journal on Optimization, and previously served as editor-in-chief of Mathematical Programming Series B. He has also served as associate editors of Mathematical Programming Series A, SIME Review, SIME Journal on Scientific Computing, and several other journals and book series. So without further ado, let's welcome Professor Wright to give the first talk on optimization in theory and practice.
Great, thank you. Thank you, Chico. Okay, thanks so much, Kim Chuan. And I'm a little bit embarrassed as being an organizer of the workshop and giving 2 one-hour talks right at the start of the workshop. It's sort of, but it was completely out of my hands. I didn't realize these lectures were actually part of the workshop until they told me like less than 2 weeks ago. So anyway, and I apologize also if you've heard versions of these lectures before. This one I think I gave for the first time about 1.5 years ago. Of course, I've tweaked it quite often since then. And the other one I'll talk about when I come to it. I just want to say a little bit about this workshop. Thank you so much to all of you that could make it. As you know, we started planning this back in 2017. Kim Chuan took me to dinner one night in Berkeley when we were both at the Simons Institute for a program, and told me about plans to have this program here in 2020. So we invited many of you to that, and it was supposed to be, I think, at least a month long, and there were going to be 2 workshops and 2 summer schools, and a very extensive program on this very exciting area. And then, of course, COVID intervened, so we had to successively delay it until finally we're having it now. So I'm glad that we could still get many of you to come. So that's the genesis of it. I think it's still an exciting area. It was exciting when we started planning it 5 years ago, this intersection of optimization, data science, machine learning. It continues to be very current, exciting area. It's continued to develop in many ways in the last 5 years. And hopefully we'll see some of these developments here, but there are many other formats going on. There are NeurIPS workshops going on this week where they're talking a lot about this intersection between optimization and ML. Okay, so this picture, by the way, this was taken on July the 3rd this year, not by me, unfortunately. My pictures are never this good, but I particularly like it because it's beautiful. It shows the lake in Madison, and over the last 2 summers, I've become fanatical about sailing. With my colleague Rob Nowak and my colleague Jim Ludke, who many of you know. And so we take out these boats, particularly these white ones here. They're the ones that I like to go out in. And this lake is a nice big lake, and we have a fantastic time out there. So yeah, this picture is very close to my heart. Okay, so I want to talk in this talk about the interaction between theoretical complexity results in optimization and practical performance of methods, right? And we all like both of these areas. We like methods that are fast in practice. We also like proving things about them. But the two things are not completely aligned, right? So there's two aspects. They tend to drive and motivate each other, but often there's many lags and gaps. You know, the things you can prove about a method often are not as strong as the sort of performance you see in practice. And a lot of the work we do is about trying to close those gaps in different ways. When I talk about complexity, I'm mostly going to talk about worst case upper bounds on the complexity of a method. That's not the only game in town. People try to prove things about average case these days. They also talk about lower bounds, which I'll say a little bit about. But I'll mostly talk about worst case. So I'll start out with a little bit of an introduction. Much of this will be familiar to you. This talk was really, I was thinking that I was going to have a more general audience rather than an audience of optimization specialists, but you still might find some things of interest here. And then I'll focus on two areas, linear programming and then nonlinear, mostly nonlinear unconstrained optimization. Sometimes convex, sometimes non-convex. And again, a lot of what I say is going to be opinions, and of course, you might have different opinions about some of these things, which is totally fine. So these are the two problems I'm talking about, both very familiar to us. The first one, linear programming, and this is what I call standard form. People often use different, they have their own idea of what standard form is, but I'll take it to be equality constraints and non-negativity on the variables. And then unconstrained optimization, of course, we just want to minimize a function that's a mapping from Rn to R that's smooth. And in various parts of the talk, I'll assume that F is convex, satisfying this definition. Strongly convex is the same definition, but there's a quadratic lower bound with a parameter sigma, which sort of puts a lower bound on the curvature of F. And then in some cases, I'll talk about complexity of non-convex, and we've got experts on that here, like Philippe and George and several others of you, where we'll typically assume that the function is lower bounded but smooth. I'll usually assume that the gradient is Lipschitz continuous, so we call that L smooth, where L is the Lipschitz parameter. And in some cases, although I won't go into this very much at all, we can also assume Lipschitz continuity of the Hessian and maybe higher derivatives as well. Okay, so when we're talking about linear programming, of course, we all know how to write down the KKT optimality conditions for linear programming. It looks like this. They're all linear except for this complementarity condition here that says that the dual slack S and the primal variable X have to be complementary to each other. So it's sort of a set of mildly nonlinear equations, but the thing that makes it hard are these bounds. You have to, in interior point methods, you've got to keep X and S strictly positive in all components. So in talking about complexity, we have to develop these concepts of what does it mean to be an approximate solution. And in LP, an appropriate notion of approximateness of the solution is that all of the linear conditions are satisfied, those two equalities there, and also the bounds. And the nonlinear condition, which is a complementarity condition, we assume that the average of the products of Xi, Si, which is also known as the duality gap, when all the other constraints are satisfied, we assume that that has to be less than epsilon for some specified positive epsilon. Okay, so that's what it will take to mean an approximate solution of an LP. When we're talking about unconstrained optimization, there's a lot of ways that we can define approximateness of solutions in that context. So we can talk about function suboptimality. We can say, let's find a point X that comes within epsilon in its function value of the optimal function value. That's one way to define an epsilon optimal solution. We can talk about finding a point X that's within a distance epsilon of the solution set. So curly S there is the set of minimizers of F. We could talk about an epsilon first order condition, which is that, as you all know, the first order condition to be an optimal first order necessary condition is that the gradient is 0. So we can say if we can reduce the gradient below some threshold epsilon g, we'll call that an epsilon first order solution. We can also talk about epsilon second order solutions, particularly when we're talking about non-convex functions. So this is where the first order condition is satisfied, and also the eigenvalues of the Hessian are all greater than some threshold negative epsilon h, where epsilon h again is some small parameter. Okay, and why do we want to talk about approximate solutions? Well, the reason is that most of the algorithms we work with will never find an exact solution. They'll only converge to it asymptotically. And what we want to do is to figure out how many iterations it takes to get one of these epsilon accurate solutions, since we're never going to find an exact solution. An exception to this, of course, is the simplex method. So in principle, the simplex method looks at vertices of the feasible polytope and eventually finds an exact one. And Yintat's arrived just in time for me to show one of his slides. So in a few minutes, you'll recognize the slide, Yintat. But the simplex method, in principle, if you do exact arithmetic, it will actually find an exact solution. But most others will, all you can hope is that they'll output an epsilon accurate solution, where epsilon accurate in one of the senses that I've described. And often we'll be interested in, one thing we'll be interested in is how many iterations it will take to find such a solution, and how does that number of iterations depend on epsilon. So you could get dependencies like, it's order 1 over epsilon iterations, or 1 over epsilon squared. Or if you're lucky, it'll be log epsilon iterations. And often when people are talking about complexity, they'll talk about it in two different ways. And the two ways are sort of interchangeable. So you can say, first of all, you identify this quantity, let's call it tau k, which is the quantity that you're trying to drive below epsilon. So it could be a gradient, or it could be suboptimality, or whatever. And you could say, how does tau k depend on k, the number of iterations, or the iteration that you're currently at? And so there's 5 different ways that tau k can depend on k. These are the ones that you typically find happening. It could be a 1 over k dependence. It could be 1 over square root of k, which of course is slower, 1 over k squared. If you're dealing with linear rates, it's a number less than 1 to the power k, tells you how tau k is going down. If you're lucky enough to be dealing with a quadratic rate, then tau k is bounded by some multiple of tau k minus 1 squared. And then you can convert those into the question of how big does k have to be before tau k drops below epsilon. You can just put a epsilon bound on top of these quantities here on the right-hand side of these expressions that depend on k, and just solve those for k. And so, for example, if tau k is going down like 1 over k, then that means that you're going to need 1 over epsilon iterations, order 1 over epsilon iterations, to drive tau k below epsilon. And similarly, if you've got a linear rate, then you're going to need 1 over phi, where phi is the quantity that shows up here in the linear rate, 1 over phi times log epsilon iterations to get below epsilon. So you can talk about these two sort of concepts more or less interchangeably. Another question is, what sort of model of computation do you need? So if you're not interested not just in the number of iterations it takes, but how much computation do you need to get below, to get this quantity below epsilon, the traditional model was this bit complexity model, which more or less assumed that you're doing computations on it. You could reduce it all the way down to a Turing machine. And when we were working on interior point methods in the 90s, many of the papers used this model. So they assumed that all the data was rational, so that you could do, in principle, you could do all the operations exactly by doing integer arithmetic. And so this is sort of a clumsy model to work in. It's, on the one hand, it's rigorous. On the other hand, it's certainly not how people implement the simplex method in practice. So Bloom, Shub, and Smale came up with this model in the 90s, which is much closer to reality. It's not perfectly aligned with reality of computation on digital computers, but you could argue that it's much closer. The so-called real number model, and it's a very simple model. It just assumes that you're working with real data. So if you're dealing with a linear program, the matrix and the vectors in the linear program are all real numbers that require, say, 1 unit of storage. And every time you do an operation, plus, minus, multiply, divide, inversion or whatever, with 1 or 2 real numbers, that takes 1 unit of computation. So that was their model. And obviously on a real digital computer, we're doing floating point arithmetic, so it's not exactly that, but it's fairly close to reality, and it's much easier to analyze. So for example, if you're doing an interior point method for LP, where at every iteration you're solving a linear system of equations that has dimensions order n, and if you assume that you do that exactly, the number of operations you need to do that would be order n cubed, naively, okay, if you were doing dense arithmetic and everything. And so this, as we'll see a little bit later on, this is why when you look at interior point papers from the 90s, you'll often see bounds on the complexity, on the computational complexity that look like this. They're order n to the 3.5 log epsilon up to, say, n to the 5 log epsilon. And order n cubed of that just comes from solving a linear system. And the rest of it comes from the number of iterations you need to get epsilon accurate. Okay, so simplex method for LP. Now, of course, as you all know, the simplex method was first developed in the 1940s, and it's still a very powerful method in practice for solving linear programs of all sizes. And interestingly, there's never yet been a truly polynomial worst case bound for a simplex method. In fact, there's this famous worst case example of Klee and Minty in 1972, which basically shows that for a standard rule that you use to select the pivots, you're going to need exponentially many pivots in the dimension n to find the solution. So this is really maybe still the outstanding example of a wide gap between the complexity theory for an algorithm for a particular class of problems, namely simplex for LP, and the practical performance. And people have been very interested in closing this gap. One early approach in that line was Borgward did some work in the 80s. He actually has a book on so-called average case analysis, where he says if you draw the data for the LP from a certain distribution, then on average, in some sense, expectation over the distribution of the data, the number of pivots you need is only polynomial. But Spielman and Teng did this very important work about 20 years ago on so-called smooth analysis. So their viewpoint there was, okay, if you give me an instance of an LP, I'm allowed to make random perturbations to the input. So I'm not going to solve the problem that you give me. I'm allowed to make little tweaks to little random tweaks to the input. And what they can show is that the expected performance under those small tweaks that I can make ends up being polynomial in n. Okay, so even if you give me a bad example like the Klee-Minty example, I'm allowed to tweak it a little bit, and what I get in expectation under those tweaks is something that is polynomial. It's also polynomial in the size of the tweaks, the standard deviation of the tweaks. So basically the message here is that there are bad examples, but they're kind of isolated in the sense that if you can perturb them a little bit, you'll perturb away to a nice example. Okay, but of course, the excitement in linear programming was finding other methods other than simplex for which you could prove worst case complexity bounds. And the first one of these very famously was the ellipsoid method of Khachiyan. That turned out not to be practically useful. But then the projective method of Karmakar came along in '84, and that was a real breakthrough. He claimed that it had good practical performance. It actually isn't very good, but other people got working on this whole thing, realized very quickly that was related to log barrier methods, which go back to the 1950s. And then over a period of about the next 5 or 6 years, primal dual interior point methods emerged as a very powerful class of methods, which not only worked well in practice, but you could also prove beautiful, elegant, elementary polynomial complexity theory about them. And the basic idea is that you go back to those KKT conditions that I showed you a few slides ago, and instead of insisting that the product of the xi and the si be 0, you actually target another point where that product is some parameter mu, where mu is some positive quantity. And you apply Newton's method, just reminding you what that system was back here, this system here. You just replace the 0 here on the right-hand side by mu, and you take Newton steps on the resulting square system of linear equations. You just generate, well, it's actually nonlinear. You generate Newton steps. You make sure that the steps maintain positivity of the components of x and s. And you might take multiple Newton steps, maybe just a few, and then you decrease the mu, reset the target, and then take some more Newton steps. So basically, it's like a continuation strategy for approaching the optimal solution along a sort of central path, and the central path is defined by positivity of the mu. So that's the idea. And there's this era when the classical theory for these methods was produced, a fairly short period, when people figured out that you could prove that the number of iterations was somewhere between n to the 1/2 log epsilon and n squared log epsilon for different variants. Many of us sort of got a little bit suspicious of complexity theory because there was almost an inverse relationship between the power of n that appeared in the complexity analysis of these methods and the usefulness of the method. So the ones with n to the 1/2 log epsilon were things like predictor corrector that used these very tight L2 neighborhoods, which actually weren't very good in practice. Whereas the n squared log epsilon ones were the infeasible interior point methods that people actually implement. So that sort of made us suspicious about the usefulness of this kind of theory. But from a theoretician's point of view, there's very little difference between n to the 1/2 log epsilon and n squared log epsilon. It's sort of pretty much the same to theoreticians. And also people observed in practice that there was only a very weak dependence on n of the actual number of iterations that were taken on real problems. So that, pretty much any LP, it's somewhere between 10 and 100 interior point iterations is enough to solve it. The other nice thing about this theory is it's very elementary. So in one of my graduate optimization classes, I can basically teach a complete theory for a path following type, long step path following interior point method in one lecture. Okay, so recently theoretical CS people who also do optimization have gotten very interested in trying to improve the complexity of these methods, and unfortunately my information is not up to date, but Yin Tat is here, so he's going to, I'm sure he can tell you all the latest in this line of work, but my information is kind of current as of a year ago, I guess. And I've listed some people here that work on this stuff. So they essentially try to they come up with new variants of interior point methods. They sort of enhance the standard interior point method in various ways. And they express the complexity in terms of the number of matrix multiplication type operations you need to run the whole algorithm. So they take the matrix multiplication as kind of the unit of work and try to figure out how many of those you need to solve the problem. It's also tied to the number of non-zeros in the matrix A, which is good because most LPs have sparse matrices. And in fact, what they can show is that LP complexity has almost caught up to matrix multiplication. Has it caught up yet, Yin Tat? Yes. It hasn't, okay, but almost, okay? So here's Yin Tat's slide, and I think this was current as of a year ago. Has it changed since then? Not very much, okay. So this slide, there are two lines. There's a red line and a blue line. The blue line is the best known, I believe, the best known complexity for multiplying two n by n matrices. And as you can see, the standard, if you just do the most obvious way of multiplying n by n matrices, the standard complexity is order n cubed. But then, who was the first one that reduced it below that? Strassen, that's right. Strassen in the 70s or the 60s came up with this method that was subcubic. It was like 2.7-ish, 2.71 or something. And it was based on breaking the matrix down into 2-by-2 blocks and showing that you could multiply two 2-by-2 matrices. You didn't need 8 multiplications, you only need 7 or something. And applying that principle recursively, you could reduce the overall complexity. And since then, people have chipped away at it. And I believe the current complexity is about 2.38, but people believe that you can eventually get that down to 2, okay? Do TCS people still think that? You can do it in 2? Who knows? Okay. And then, and the red line is linear programming, okay? So the dependence on n of the complexity of solving an LP. And of course, it started out, if there's n over here, that means exponential, essentially. And then Kachian reduced that, and Kamakar reduced it further, and it's been chipped away at ever since. And then this is the recent work that's been done where they've essentially got it down to, now it looks like it's below the cost of a matrix multiplication, but these last few steps assume that the complexity of matrix multiplication is 2. So assuming that that's the case, they can show that LP, you can do it in 2 plus 1 over 18. Is that still the case? Okay, good. I'm glad we have an expert here to refer to. But okay, so how do these things work? So this is my kind of outsider's high-level view of the sort of approach they take. First of all, they don't solve the Newton steps exactly. They're only computed approximately. The second thing is that they realize that the change in the matrix that you have to solve to get the Newton step, it doesn't radically change from iteration to iteration because the A and the identities are the same. All that's changing are the X and S components, and some of those are not changing very much, so there's only really a low rank change. So they don't have to refactor that matrix from scratch to compute the Newton step. They can just make a low rank update. So, that's a important observation. Another thing is they don't follow the traditional central path necessarily. They have ways of weighting the central path. And then there are some methods like the sort of work a few years ago of Alexander Madry. He just worked on particular variants of LP, like max flow problems. It wasn't for general LP. But more recently, Jan van den Brand, I'm not sure if I'm crediting, there might be other people that worked on this as well, sort of came up with a very specific way of manipulating the data structures to show that you could do this updating of the factorization very efficiently. So they really paid attention to how did you actually manipulate the data structures to do this in an efficient way. And I found that fascinating because we used to think, those of us that worked on scientific computing in the 80s and 90s, including me and Philippe and other people here, we used to think of this business of manipulating data structures as sort of a grungy numerical implementation issue that you only sort of got into if you're writing software. We never thought that theoretical CS people would sort of home in on this as a really key issue. How do you maintain matrix factorizations efficiently and so on? But it really is a key issue. In fact, there's a whole series of workshops at Simons next year that INTAT's involved in organizing that are focusing on this issue of how do you manipulate data structures to achieve high efficiency in these methods. Okay, so are you going to be talking about this stuff? Good. Okay, so you'll hear much more from INTAT later in the week. All right, so let me switch gears a little bit to nonlinear optimization. So this is just minimizing f of x. Now, as you know, with nonlinear functions, it's harder to talk about arithmetic measures because different nonlinear functions can take vastly different amounts of arithmetic to evaluate. And also, if you're interested in their gradients and their Hessians as well, they can also be very simple to compute or very complicated, depending on what f is. So Nemirovsky and Newton came up with this oracle model in the 80s, and I'm quoting from the English language version of their book. I think the Russian one came out a little bit earlier. So they defined this concept of an oracle, which is a unit of information about a function. And different algorithms make use of different oracles. So an oracle could just be the cost of evaluating a function. You give the oracle a point x, it tells you what the value of f of x is at that point. Other algorithms that maybe use gradients, the oracle is now the function value and the gradient, okay? Or it might just be the gradient. Or it might just be an unbiased estimate of the gradient. So in stochastic gradient, that's the oracle model that they use, is that you give it x to the oracle, it comes back with a vector g that's an unbiased estimate of the gradient. And so you can talk about the oracle complexity of methods, which is how many of these oracle calls do you have to make for a specified oracle to get an epsilon approximate solution. And some people use this term evaluation complexity, which is quite similar, and that is there's something that we're evaluating, like a gradient or a gradient and a function value, and the evaluation complexity is how many of these evaluations do you need to come back with a epsilon accurate solution. Now, iteration complexity is another concept, and this is the one that I've talked about already. This is just how many iterations of your algorithm do you need. And that one is a little bit dicey because different algorithms can perform vastly different amounts of work per iteration. So obviously it's going to depend on the complexity of the function, but also some methods might require you to solve a sort of a complicated subproblem, like minimizing a cubic or or solving a truss region problem or something, where it's hard to nail down the complexity of that subproblem. And so for me, it's sort of more appealing to sort of drill down into the complexity of the subproblem and try to get a handle on that when you're talking about worst case complexity. Okay, so upper and lower bounds. I'll say a little bit about upper and lower bounds here. So most of the focus is on upper bounds, that is finding a worst case bound possibly for a given algorithm or possibly for an entire class of problems. But there's also been some attention recently on lower bounds. So what do I mean by lower bounds? Well, in lower bounds, you typically work with a given problem class and a given algorithm class. So your problem class just might be, convex, smooth functions, very smooth functions. And your algorithm class might be, you get access, the oracle consists of a function value and a gradient, or maybe just a gradient, okay? And a lower bound says, okay, if you take any problem, a lower bound says there is a problem in the problem class for which all algorithms in the algorithm class require at least this many calls to the oracle to find an epsilon approximate solution. So essentially it's kind of a worst case problem from the specified problem class. That any algorithm that uses oracles of the specified oracle in that worst case problem is going to take at least this long. And so-called optimal methods are methods that achieve that lower bound, for which the upper bound, the worst case upper bound, coincides with the lower bound to within some constant factor. And the classic example of that is Nesterov's accelerated gradient method. That's an optimal method for convex smooth minimization. So the problem class in this case would be minimization of convex functions with Lipschitz continuous gradients, and the algorithm class would be the class of methods where the kth iteration lies in the span of all the gradients that you've encountered up to this point. Okay. Now, a little bit of a diversion here. Probably everyone in the room knows what a gradient descent method is. It's just a method that moves in the negative gradient direction. Momentum methods, the heavy ball method is the classical momentum method dating back to the 70s. And this is where you modify the gradient method by also adding on a multiple of the last step the previous step that you took. And Nesterov's accelerated gradient, it's related to the heavy ball method. The trick there is that you don't just evaluate the gradient at xk, you actually evaluate at this intermediate point. So you take the momentum step and evaluate the gradient at that point. And of course, there are many other variants of these approaches. But maybe the classic worst case example for the class and algorithm class, the problem class and algorithm class I was just talking about, this is in Yuri's book from 2004. I think it appeared earlier in a paper. It's this very simple quadratic where it's a convex quadratic where the Hessian is tridiagonal, and you start from a particular point. You start from 0, and the linear term, by the way, just has a single non-zero here. Oh man, better be. Okay, it just has a single non-zero, and you start from 0. So you can show, using a sparsity argument, you can show if your algorithm is generating iterates that lie in the span of all the gradients up to iteration k. So xk lies in the span of all the gradients between iteration 0 and iteration k. You can show by a sparsity argument that after k iterations, you must be at least this far from the solution. So xk minus the optimum, by the way, is completely dense. It fills in. After k iterations, you cannot have filled in more than the first k elements of x. And so you must miss out at least on the last n minus k elements. And so you can show that the distance from the solution is bounded below by 1/8 of the distance between the initial point and the solution. On the other hand, you can show that and a consequence of that is that the distance of f of xk to the optimal value of f is bounded below by 1/k² times a constant. On the other hand, you can show using a worst case analysis that there's an upper bound on f of xk minus f star that's also 1/k². And so the upper and lower bound coincide to within a constant factor. So this is not fully satisfying to me because it only works up to for k less than n/2. So this argument based on sparsity only works when you've certainly taken less than k iterations, less than n iterations. Peter, do you know if there's improvements on this sort of thing? Do people prove lower bounds that go beyond n iterations? Or don't you care about lower bounds? Okay.
After n, you can do.
What's that? After n, you can do what?
After n iteration, you can.
Okay, so you can still say something. Can't really go beyond n, okay. There are people like Blake Woodworth, who was a student of Nadi Srebro, who graduated last year. He wrote a whole thesis on lower bounds, which is a very powerful thesis, a very deep result. I had a quote by Aaron. I think it's on the next slide. Oh yeah, I wanted to. I did some actual computations with this based on Uri's example, that worst case example that I just showed you, where n is 100. So I coded up gradient descent with a constant step length, gradient descent where you actually minimize along each negative gradient direction. They're the red and green lines. The blue line is Uri's method, and the light blue line is conjugate gradient. We all know that conjugate gradient is exact on quadratic functions. It converges in n iterations. And you see that here. That's got a zero error after n iterations. But in this one, accelerated gradient actually was better than the variance of steepest descent. But then bear in mind that Uri's example is actually strongly convex, and he's got a variant of his accelerated gradient that works on strongly convex functions, and it's provably linearly convergent. And the interesting thing is when you code up Uri's method that exploits the strong convexity, it's actually slower on the first n/2 iterations than just naive steepest descent, and certainly a lot slower than conjugate gradient. Of course, it catches up at some point when you get out to n iterations and beyond. Then accelerated gradient catches up to gradient descent. But I guess the story here is that this complexity analysis, lower bound and upper bound, doesn't give you a complete picture of what these algorithms are doing, and it doesn't. If you just make a decision to use an algorithm based on the theoretical complexity, it may not be an optimal decision for the context that you want to use it in. So Aaron Sidford has this quote, when people like me complain about lower bounds not being maybe super interesting, Aaron says, well, without a lower bound, how do you know if you found the right answer, right? In other words, you can't claim that your algorithm is a good algorithm unless you prove that its complexity is almost as good as the known lower bound. So when there's a gap between upper and lower bounds, or when your algorithm doesn't quite achieve optimal complexity on the lower bounds, you can play some games to make it look better. So of course you can try to narrow the gap between the upper bound and the lower bound by improving the upper bound. You can try redefining the problem class that you're working with to sort of, it's like putting a cut into to cut off a region of infeasibility. You can shrink the problem class to exclude the bad example, right? Say, okay, I'm going to work on a narrower problem class that doesn't include this bad example, and on that problem class, the upper bound is nicer. Or you can do things like look for other concepts of complexity other than worst case, like you can try to prove something about average case, or you can do smooth complexity, which is a very powerful concept. Okay, I want to keep an eye on the time here. Yeah, okay, so just a little bit of a mea culpa about those of us that are kind of older people that did work in optimization in the 80s and 90s and so on. We tended to prove sort of two kinds of results, those of us that weren't living in the Soviet Union at least. So we would prove asymptotic complexity. That is, we would prove that our favorite algorithm for unconstrained or constrained minimization, if we started from a fairly reasonable starting point, we don't typically put many restrictions on the starting point, we can show that asymptotically it will find a stationary point. If you let the algorithm run forever, it might find a stationary point, it might find a KKT point in the case of constrained minimization. If you're doing a truss region method, it might even find a second order necessary point. But we couldn't really nail down the number of iterations that you needed to get close to such a point. We would just say in the limit, it will end up at a point like that if it's allowed to run forever. And the other kind of convergence analysis we would do is to say, okay, if you start close to a solution, a local solution, maybe satisfying strong properties like constraint qualification, second order sufficient conditions, and so on, then we can prove that our algorithm converges linearly, maybe even superlinearly or quadratically. Okay, so these are the two flavors of results that we would typically prove, those of us that didn't live in the Soviet Union at least. So with some exceptions, of course, people that worked on linear programming proved these sort of global complexity results. But by contrast, the sort of analysis I'm talking about today is about finding a global rate. That is, if we start from a reasonable starting point, we can prove something pretty strong about how much improvement we can make on every iteration. And that is the thing that allows us to sort of put upper bounds on the total number of iterations we need to get a result. So if you look in the first edition of my book with Jorge, and even in the second edition, it's mostly got results of those two flavors that I mentioned, except, of course, in the chapter of interior point for linear programming. And this kind of theory is it tells you something about how practical methods behave, but of course, it doesn't tell you everything. Complexity analysis is sort of another kind of analysis. It can tell you a little bit more. Again, it doesn't tell you everything, but it sort of, gives you more information about how methods work. So this is where, some of my opinions come in, and my information here might not be completely accurate, or your mileage may vary, but certainly before 2008, theoretical CS people have always been interested in the complexity of LP. That's always been a benchmark problem to theoretical computer scientists. They've been beating away on variants of the simplex method for a long time, trying to find pivot rules that can get better complexity. Within the optimization community, of course, even before 2008, there was all this work going on in Soviet Union. I've mentioned Nemirovsky and Yudin, with their idea of oracle complexity. And even those of us that worked on interior point methods, of course, we would always have a section in our paper where we'd prove a complexity result, including those of us that came from a nonlinear optimization background. So then some very influential books appeared. This very influential interior point book of Nesterov and Nemirovsky was published by SIAM in 1994, and that really promoted this global complexity perspective. They showed that if you had self-concordance, the self-concordance property in constrained convex optimization, you could prove global complexity bounds on how many iterations you need to find an exact solution. And then Boyd and Vandenberg came along with their convex analysis book, and they really adopted some of that perspective that was pioneered by Nesterov and Nemirovsky. So if you look at Yuri's book from 2004, I haven't updated this slide recently, but he wrote this book, which has now become very well known, although it took a while before people started paying attention to it. It grew out of lecture notes that he'd been using in Belgium. It really did deal quite a lot with complexity of nonlinear convex optimization, including problems where there was some sort of structured non-smoothness. And you can see the explosion in citations of that. If you read the preface to the book, it's very interesting. He sort of points to Karmakar's paper as being the genesis of when optimizers sort of got interested in the relationship between complexity and practical performance. So he has this quote that the most surprising feature of Karmakar's method was that the theoretical prediction of high efficiency was supported by computational results. This fact dramatically changed the style and direction of research in nonlinear optimization. And I think he was being a little bit prescient there. This is, Yuri writing in 2004. I don't think it was till some years after that people really got, interested in the mainstream optimization community and suddenly proving complexity results. But he certainly was prescient enough to see that as a future direction that people would get interested in. Okay, so what changed after 2008? I sort of picked 2008 as more sort of arbitrary date when mainstream optimizers got interested in these issues. One thing, a little bit self-serving here, but Katja and I and Kristen Bennett organized a stream of workshops at the 2009 ISMP, and we deliberately, in each of these sessions, we had people from ML and people from optimization, and that sort of cross-fertilized a lot of the interactions that now are very ubiquitous between machine learning and optimization. There was this paper of Nemirovsky, George Land, Judiski, and Shapiro from 2009, where they studied stochastic gradient, and that appeared in SciOpt, and it came along at an incredibly important moment when stochastic gradient was really emerging in the ML community as the essential algorithm. I mean, it is the workhorse algorithm in machine learning. And they just happened to publish this paper, and I think you didn't really realize at the time, George, that it was being used so widely in ML. But so it just came along at this very fortuitous moment. And then, of course, in the years since then, a lot of people from ML have gotten very involved, and a lot of people from theoretical CS have gotten very involved in optimization, and they brought with them their interest in complexity issues, and that sort of changed the culture of optimization largely. And then there's this growing interest in complexity for non-convex optimization. So I think we can point to this paper of Nesterov and Polyak from 2006 as being a very influential one. I know, Philippe, that probably is the paper that spurred your interest in this area. Maybe. Yeah. So that's what Philippe and his collaborators, Nick Gould and Kourakatis, got very interested in complexity of non-convex optimization, and then I sort of discovered it somewhat later, and various other people. And the other thing that's sort of spurred a lot of interest in non-convex optimization is that really in the last few years in machine learning, people have identified wide classes of non-convex problems that are actually easy to solve. Now, we used to think in non-convex optimization that these were just incorrigibly hard problems. There was never any hope of being able to find sort of efficient algorithms that you could prove interesting complexity results about. But it turns out there are entire classes of problems in low-rank matrix optimization, for example, where they have certain features that make them easy to solve in some sense, even though they're non-convex. Okay, a few words here about a stochastic gradient, because this has been an area that several people in the audience have contributed to enormously. In particular, the convex finite sum problem. This is ubiquitous in machine learning, where the objective you want to minimize is the average of a bunch of individual objectives. Typically here, the x's are parameters from some statistical model, and typically each of these functions, fi, depends on a single item of data. So fi tells you, for that item of data, and for this setting x of model parameters, how good a job the model is doing at predicting the output. So if it does a perfect job of predicting, the fi is often 0. If it doesn't do a perfect job, the fi is often positive. So this is a very natural kind of problem to apply stochastic gradient to, and because in stochastic gradient, well, first of all, if you just do a gradient method for this, you have to evaluate, to get the gradient of f, you need the gradients of all of the fi's. And if n is in the millions or billions, that's extremely inefficient. You have to scroll through the entire data set. But stochastic gradient is a fantastic fit for this problem because it can give you an unbiased estimate of the gradient if you just pick one of the i's at random, or you pick a batch of i's at random and just evaluate the gradient of fi's just on that batch. Okay? And you know, the analysis of this, it goes back to the 1950s, but you can read George's paper with Nemirovsky and Judiski and Shapiro for a very cogent analysis of that case. Now, later on, people came along with ways of improving the variance. You can see that if you just pick a single I, you're going to end up with an unbiased estimate, but its variance is going to be huge. That is, it could be very far away from the true gradient. And so people came along with methods that sort of hybridize between full gradient methods and stochastic gradient methods, where they can prove better complexity results, and on some problems they get better practical performance as well. So another class of methods, coordinate descent. Again, this is something I worked on a while ago, and several other, Peter's worked on this a great deal, where you just pick one component, or maybe a small subset of components of X, to update at each iteration. You can either try to explicitly optimize over those components at every iteration, or you can take just a step in the partial gradients with respect to those components. Now, there are different ways you can select those components. You can select them randomly. You can select them systematically in some way. You can cycle through them. You could do this thing called random permutations, where you shuffle the coordinates and then work through them in the shuffled order, and then reshuffle them periodically. Again, this has been an area where there's a real synergy between theory and practice. That is, people have proved practical things about synchronous parallel, asynchronous parallel versions of these methods. They've also worked on how they're interested in how they perform practically on problems from ML. And there's a lot of back and forth between the theory and the practice in this area. So that's one area where theory and practice have kind of tended to drive each other. Another area is in parallel methods for these kinds of finite sum problems. So this Hogwile paper of mine with Ben Recht and Chris Ray and Feng Nu from 10 years ago, or more than 10 years ago at NeurIPS has become very influential. of course, all of this goes back to Bertzakis and Tsitsiklis's book now from 33 years ago, where they described asynchronous and synchronous parallel versions of optimization methods. They weren't very interested in complexity, but certainly they knew how to describe these methods and analyze their asymptotic convergence properties. And several of us here have worked very heavily in these areas. Nowadays, there's this whole area of federated learning, which is sort of just a largely, maybe Peter will disagree with this, largely just a parallel SGD. What's that? Good. Okay. Well, you get to talk later on, so you can describe that. Okay, and there's a lot of in federated learning, there's a lot of complicated issues about how do the different processes that are working on these problems, how do they communicate, how much computation do they do in between communicating stuff, what are the communication patterns and so on. So there's a lot of interesting stuff here. The comment that I make here, certainly about this earlier work, is that the practice tends to drive the theory. So certainly in the Hogwile paper from 2011, we were just implementing this crazy method that sort of did this asynchronous stochastic gradient. And then we decided to try to come up with a model that more or less captured what we were doing and prove stuff about that. And that's, I think, also been the approach of several other people. Okay, a little bit about this concept of benign non-convexity. As I've said, there are a whole class of problems from ML, particularly low-rank matrix problems, and of course pioneers in this area are our colleagues Sam Bura and Renato Montero, who came up in 2003. They said if you can take a semi-definite program, you know it's got a low-rank solution, so let's just make an explicit low-rank parameterization. Let's just express the unknown X, the matrix X, as an outer product of two skinny matrices. And what we get is a non-convex problem, but they showed that it's not very hard. And of course, there have been many other works since then in many different areas. Phase retrieval, this idea of low-rank matrices has been extended to low-rank tensors. These AC power flow problems, again, non-convex problems with quadratic constraints. Stephen Lowe and collaborators have showed that some interesting instances of those problems are benignly non-convex. Ju Sun has this excellent page where he keeps track of all these different benignly non-convex problems that are showing up, which I've got a reference to there. And also in machine learning, one of the overriding issues of the theoretical neural nets these days is to understand why over-parameterized neural nets, if you train them long enough, and it may be a very long time, but if you train them long enough, they'll actually find a zero-loss solution. They'll perfectly fit the data. And I think it's fair to say that some people have partial explanations of that for simple architectures, including I'm on several papers like that. But a paper that really captures the practical reality is, I don't think that's happened yet. Okay, a little bit here. I'm starting to get low on time, so I'll probably skip over some of this stuff. But in low-rank matrix problems, here are some of the sort of features of those problems that make them benign. So some problems have this property that, yes, they have multiple local solutions that are possibly separated. They don't form a contiguous set. But you can show in some cases that all the local minima are global minima. They all have the same function value. So any one of them is as good as another in some sense. Another property that some of these problems have is that all the saddle points are strict. So you can have points where the gradient is zero, but at such points, the Hessian has a direction of strict negative curvature. So if you've got an algorithm that can exploit that, for example, algorithms like the ones I work on where you actually look for the negative curvature directions, then you've got a way of getting away from those saddle points and potentially going to actual local minima. There are problems where this so-called PL condition is satisfied. This is where you can bound the suboptimality in F by some multiple of the gradient. There are problems that satisfy this regularity condition. It looks kind of weird, this property that the grad F transpose X minus X star is bounded below by the sum of X minus X star squared and the gradient squared. Turns out a lot of interesting matrix optimization problems have that property, and you can use those to prove linear convergence of like gradient type methods. And the last one that's also very important, particularly again in low-rank matrix problems, is that some of those problems, by using the properties of the problem, you've got a very intelligent way of choosing the initial point that puts you close to a global minimum. So if you just use that technique to choose the x naught, you can then just run steepest descent and it will find the minimum efficiently. So these are all different sort of features that these problems have that will let you show that despite their non-convexity, you can find solutions efficiently. So I've got a few slides here on matrix sensing. I think this is an example of a problem where it's you've got a symmetric matrix is the unknown, but it's a low rank symmetric matrix. So you can parameterize it explicitly by a ZZ transpose, which is the outer product of a Z with itself, where Z is this long skinny matrix. You get a non-convex problem, which is this problem down here. It's non-convex in Z, but you can show that under certain assumptions on the sensing matrix AJ, if you make certain restricted isometry assumptions on the matrix that is sensing the properties of X, you can show that all the local minima are in fact global, and all the stationary points that are not I don't know, that's sort of garbled, but all the saddle points have negative curvature direction. So those properties sort of tell you that it's a benignly non-convex problem. And moreover, there's an efficient way to initialize. You can show that if you just take this very clever, you form this very clever sum, which involves the observations yj and the sensing matrices aj, the sensing operators aj, that gives you an excellent starting point. Neural nets, this is again a dated slide because people are working like crazy on this problem, using all different kinds of perspectives on showing why neural nets converge to zero loss if they're over-parameterized. Misha Belkin at UC San Diego has done a lot of work on this. Peter Bartlett and his collaborators have also come with a different perspective. Wayne at Princeton uses gradient flow type and mean field perspectives to show that if you take continuous limits of certain over-parameterized nets, you can converge to a solution. It will converge to a zero loss solution. We've done some work building on that as well, so I won't say too much more about that. This is work, just a little bit of a mention here on what we can do these days about non-convex functions. This is going back to this paper of Nesterov and Polyak, and they showed that if you take the Newton model, a quadratic Taylor model, and add on this cubic term, this very simple cubic term at the end here, 1/2 MP cubed, and solve that problem at each iteration, provided the m is an upper bound on the Lipschitz constant for the Hessian, they show that you can find an approximate second order point in a specified complexity that depends on the epsilon that parameterizes the second order point. So this is something that Philippe picked up on. Philippe has a new book on this topic with Cora and Nick, a whole book on, I guess it's not just non-convex, but is it non-convex or non-convex? Constraint and also higher order, right, where you go to higher order beyond the Hessian and so on. Our late colleague Andreas Grievank had actually proposed something like this method much earlier in 1981. His motivation was mostly practical rather than theoretical. But this was never published, but he had a tech report that he first told me about that in 1986, where he had a very similar idea. There have been other approaches in recent years that some of us here have worked on. I won't talk much about those, except that I did some recent work with Mike O'Neill, where we applied these sort of gradient negative curvature methods to low-rank matrix problems that satisfied this regularity condition that I mentioned a few slides back. This one here, the last formula on this page. And we show that you could actually get a log epsilon rate. So you can improve from getting epsilon to the -3/2 or whatever to log epsilon if you apply it to these, benignly non-convex low-rank matrix problems and exploit the properties of those particular problems. Just the last few comments on, there's a lot of work to be done in nonlinear, non-convex optimization. There are very important methods in these areas where there are big gaps between the theory and the practice. So, for example, limited memory quasi-Newton, LBFGS, a very important method in unconstrained non-convex optimization. But very little is known about it theoretically. Essentially, you can show that if you apply appropriate safeguards, that it's not too much worse than gradient descent. That's pretty much all you can prove, I think, from a global point of view. And in practice, of course, it's much better than gradient descent. Also, it's been known for a long time that nonlinear conjugate gradient applied to quadratic problems has these incredibly powerful properties. There's a whole chapter in my, or half a chapter in my book with Jorge about that. But it's been known since Nemirovsky and Uden that there are worst-case examples where it's as slow as gradient descent, at least a nonlinear extension of this to general nonlinear problems. There's been some work by Steve Vavasas and his collaborators on trying to enhance nonlinear conjugate gradient with accelerated gradient, switching between the two, and getting some sort of practical, getting some sort of nice optimal rate for that sort of a method. But still, it's a sort of unsatisfying gap because nonlinear CG often in practice is much better than steepest descent, and yet we really can't prove that much about it. Another point to make before I finish up is that just because your method is great theoretically doesn't necessarily mean it's going to work great in practice. And of course, Katian's ellipsoid method is an example of that. Another method that I like to mention is this sorting network idea. So sorting networks are a very simple construct where you put in a list of n numbers, and by doing pairwise comparisons between pairs of these numbers, eventually you can, and sort of building these into a network, eventually you can output the numbers in sorted form. And there are very simple ways of doing this, these so-called bitonic networks that are exactly what you'd imagine, where you sort of do it recursively, sort of like quicksort or something. And you can show you can do it in order n log squared n comparisons. But they're not optimal. It turns out there are a class of networks that can do it in order n log n. But the disadvantage of that is that there's a constant term in that order n log n, which is 10 to the 60. So you gain a factor of log n, but you lose a constant of 10 to the 60. So how big does n have to be before you come out ahead? N has to be e to the 10 to the 60, which is like an incredibly large number. So again, these are not the sort of networks you'd ever use in practice, but they have theoretical interest. Okay, and okay, I can sort of jump. I can sort of skip this stuff, but I think closing the gap between theory and practice there's a lot of work to do in non-convex optimization and closing that gap. I've got some examples of stuff we did on with Ching Pei, who's here on random coordinate descent with random permutations. That's something that we beat on for a few years and was a lot of fun. And just concluding then, there's a quote from Fletcher's book on optimization of 1987. I liked it so much I quoted it in the preface of the book with Jorge, which is where he says that optimization is a fascinating blend of theory and computation, heuristics and rigor. And that's sort of been the theme of this talk, that there's a theoretical aspect, there's a computational aspect. We try to make those things as consistent as we can, but there are gaps, and we sort of like to use them to drive each other as we go. And I think that whole area has become much richer with this influx of problems from machine learning. That complexity theory has attained a new prominence, and all the research that's based around trying to prove things about the theory and make it work well in practice has given rise to a lot of interesting work. So I think I'll quit at that point. Thank you very much.